Alright, let's go. Number 10. The kitchen table double slit. In 1999, Marcus Arndt and Anton Zeilinger at the University of Vienna were not trying to overturn anything. They were doing molecular beam work, heating a source, collimating a beam, checking whether the apparatus could handle something heavier than an atom. The molecule they picked was carbon-60. Buckminster-Fullerene's suit, essentially, 60 carbon atoms welded into a football. The rule they expected to confirm is the one you already believe. An object with a definite size and position goes through one gap or the other. Not both. Carbon-60 is a thermal object, 720 atomic mass units, leaving the oven at 900 Kelvin, glowing in the infrared as it flies. 2 slits, 2 stripes. They got fringes. Each molecule arrived at the detector as one dot, one at a time, and the dots piled up into an interference pattern that only exists if each molecule passed through every slit at once. Arndt, Nyers, Vos-Andrée, Keller, van der Zouw, and Zeilinger published it in Nature on the 14th of October 1999, grading period 100 nanometers. De Broglie wavelength, 2.5 picometers, 400 times smaller than the molecule doing the interfering. By 2019, Fine, Geyer, Zwick, and Arndt had pushed it to molecules of 25,000 atomic mass units. 2,000 atoms. 1 superposition. The explanations came in order and died in order. Detector patterning. Akira Tonomura's 1989 electron experiment in the American Journal of Physics had already filmed fringes assembling out of nothing, dot by dot. Hidden definite trajectories, de Broglie, Bohm mechanics supplies them, at the price of instantaneous influence across any distance. Decoherence. Hacker-Miller confirmed in Nature in 2004 that heating carbon 70 to 3000 Kelvin destroys the pattern, which explains why fringes vanish and nothing about why one dot lands where it lands. Every atom in your hand is the same kind of object, not behaves like. Your hand has a location only because the room interrogates it continuously with photons and air. If contact with an environment is what fixes a position, what fixed anything's position before there was an environment? Watching does not only fix an answer, sometimes it sets the pace. Number 9. The reaction that stops when you watch it. In 1989, Wayne Itano, Dan Heinzen, John Bollinger, and David Wineland at the National Institute of Standards and Technology in Boulder were doing clockwork. Trapped beryllium ions, an RF pulse to drive a hyperfin transition, a laser pulse to count how many had moved. Ordinary metrology. They decided to check an odd prediction Misra and Sudarshan had made in the Journal of Mathematical Physics in 1977. The standard picture is clean. Apply the driving field for the full period, and the population transfers with near certainty. Measurement afterwards reads out what already happened. Reading is bookkeeping. Bookkeeping does not change the books. Pulse the readout laser during the transition, and the transition stops. Not damped. Not slowed by friction. Frozen in proportion to how often you look. Itano, Heinzen, Bollinger, and Wineland. Physical Review A, Volume 41, 1990, around 5,000 beryllium-9 ions, a 256 millisecond RF pulse. 1 measurement pulse, transfer near unity. 64 measurement pulses, a few percent. Then the objections. The laser is just perturbing the ions, nothing quantum about it. Leslie Ballantyne argued that in Physical Review A in 1991, and the argument never closed. It only works in clean 2-level systems. Fisher, Gutierrez Medina, and Raisin published sodium atoms tunneling out of an accelerating optical lattice in Physical Review letters in 2001, where frequent measurements slowed the tunneling and rarer measurements sped it up. The anti-Zeno effect. It will never touch chemistry. Kaufman and Kurisky showed in Nature in 2000 that anti-Zeno is the generic case for decay into a continuum, and Oleg Prejdo applied it to reaction rates the same year. The rate at which molecules react is not a property of the molecules alone. It depends on how often their surroundings interrogate them. Your body is one continuous interrogation of its own chemistry, never once looking away. If observation can hold a reaction still, which reactions inside you are running at the rate the environment permits rather than the rate physics prefers? Look hard and you change the rate. Look gently and you change something stranger. Number 8. The weak measurement paradox. In 1988, Yakir Aharonov at Tel Aviv University, with David Albert and Lev Vaidman, was working on a bookkeeping question in the time-symmetric formulation of quantum mechanics. Given what you prepared at the start and found at the end, what can you say about the middle? A question about accounting, not about nature. The rule being tested is the first one every physics student learns. Measure a component of spin on a spin half particle, and you get one of two numbers, plus 1/2 or minus 1/2, in units of the reduced Planck constant. That spectrum is the complete menu. Nothing else is on it. Couple the meter so weakly that it barely disturbs the particle, run it many times, and keep only the runs ending in a chosen final state. The average pointer reading comes out at 100. Aharonov, Albert and Vaidman, Physical Review Letters, Volume 60, 1988, the title states the result outright. Ritchie. Story and Hewlett at Rice University demonstrated it optically in 1991. In 2008, Hostin and Kwiat used the same amplification in science to measure a beam displacement of about 1 angstrom, 1/10,000,000th of a meter. The dismissals have all been attempted. A statistical artifact of post-selection, Ferri and Calmes built a classical model reproducing anomalous values in Physical Review Letters in 2014. Vaidman answered the field split. Noise misread as signal. The shift is systematic and scales exactly as predicted. A conditional probability with no physical referent, then Lundin and Bamber's group used weak measurement to read a photon's wave function directly off the apparatus, in Nature in 2011. And the three-box paradox from Aharonov and Vaidman in 1991, tested by Resch, Lundin, and Steinberg in 2004, one particle. Found in box A with certainty and in box B with certainty, and weak values that go negative. A negative number of particles. 35 years on, nobody agrees whether a weak value is a property of the world or an artifact of the arithmetic. How hard you look does not change the accuracy of the answer. It changes what category of answer exists. If a gentle question returns a value the object cannot possibly possess, what were you measuring? Warm, wet, disorderly systems should not permit any of this. Some of them do anyway. Number 7. The warm coherence problem. In 2007, Greg Engel, working in Graham Fleming's group at Berkeley, was running two-dimensional electronic spectroscopy on the Fenner-Matthews-Olson complex from green sulfur bacteria. A routine energy transfer measurement. The goal was to map how absorbed sunlight finds its way through the protein to the reaction center. The theory here is not soft. Wojciech Zurek's decoherence program in Physics Today in 1991 and Max Tegmark's calculation in Physical Review E in 2000 put coherence lifetimes in warm, wet biological matter between 10 to the minus 13 and 10 to the minus 20 seconds. A protein at body temperature is a storm of molecular collisions. Superposition should be shredded on contact. The spectra showed quantum beats. Cross peaks oscillating for 660 femtoseconds. The energy was not hopping at random between pigments. It was sampling roots coherently. Engel, Calhoun, Reed, Ahn, Manel, Cheng, Blankenship, and Fleming. Nature, 12th of April 2007 at 77 Kelvin. Then Collini, Kermi, Brummer, and Scholes in Nature in 2010. Reporting coherence beyond 400 femtoseconds in light-harvesting proteins from marine cryptophyte algae at 294 Kelvin. Room temperature. Panichayan-Kun and colleagues in Naz the same year at 277. The corrections arrived steadily. A pulse artifact, reproduced across laboratories and configurations. Coherence present but functionally useless. The efficiency models split and never reconciled. not electronic at all but vibrational, Duan, Prokorenko, Cogdell, Thorwart, and Miller argued precisely this in Nas in 2017, and that is now the majority reading. The problem still did not close. Shu, Jiroka, Ritz, Hoare, and Moritzen reported in Nature in 2021 that cryptochrome 4 from the European robin is magnetically sensitive in vitro, and the radical pair mechanism it depends on requires spin coherence lasting at least a microsecond inside a warm protein in a living eye. That is 1,000,000 times longer than the theory permits. A bird is using it to see a field you cannot feel, in an organ built from the same warm material as yours. If warmth destroys coherence, what is that protein doing at 300 Kelvin that no laboratory on Earth can do at 300 Kelvin? Biology may exploit the problem. Ordinary instruments cannot escape it. Number 6. The instrument that changes the answer. In 1927, Werner Heisenberg, in Zeitschrift für Physik, was defending his own formalism. He needed a physical story for why position and momentum could not both be sharp, and produced one, the gamma-ray microscope. To see an electron, you must hit it with a photon, and the photon kicks it. Error causes disturbance. Mechanical, intuitive, easy to teach. That story became the textbook rule for 75 years. Measurement error multiplied by induced disturbance has a hard floor of the reduced Planck constant over 2. You cannot read a system without pushing it, and the push obeys a fixed minimum. The specific relation is wrong. Masanao Ozawa at Tohoku University proved in 2003 that Heisenberg's error disturbance product can be violated, and derived the corrected inequality that cannot. Ozawa, Physical Review A. Volume 67, 2003. Earhart, Sponar, Suliak, Badurik, Ozawa, and Hasegawa measured the violation with neutron spin in Nature Physics in 2012. Rosima, Darabi, Mahler, Hayat, Saudagar, and Steinberg measured it with photons in Physical Review letters the same year. Both found error disturbance products sitting below Heisenberg's bound and consistent with Ozawa's. The retreats were tried in sequence. Back action only matters for microscopic things. McCuller, Barsati, and Malvolvilla reported in Nature in July 2020 that the light used to read LIGO's mirror positions physically pushes those mirrors, and measured the correlation. The mirrors weigh 40 kilograms each. Better engineering will remove it. Carleton Caves established the standard quantum limit in Physical Review D in 1981. And the only known escape, squeezed light, does not remove the disturbance. It relocates it into the quadrature you have chosen not to read. It is a classical disturbance you could calculate away. Nobody has produced a relation both universally valid and true to the intuition Heisenberg started with. Your thermometer takes heat from the water to report the water's heat. Your tire gauge releases air to report the pressure. The bill is always paid. Usually it is too small to notice. Where is the line between an instrument reading a world and an instrument helping to make one? Instruments disturb what they read. Observers also disagree about when they read it. Number 5. The disagreement about now. Between 1902 and 1905, Albert Einstein sat in the patent office in Bern, examining applications for electromagnetic clock synchronization devices. Coordinating railway clocks across long distances was the engineering problem of the decade, and it pushed a mundane question across his desk daily. How would you establish that 2 clocks in 2 towns read the same time? Newton had settled this. Time is universal and flows for everyone at once. 2 events either are simultaneous or they are not, and every observer agrees on which, regardless of where they stand or how fast they move. Einstein showed the question has no observer-independent answer. 2 events simultaneous for you happen in a definite order for someone moving relative to you, and depending on their direction. The order reverses. Zur Elektrodynamik Bewegt der Körper, Annalen der Physik, Volume 17, 1905, verified by Haffel and Keating in Science in 1972, flying cesium clocks around the world, 59 nanoseconds lost going east, 273 gained going west. Chow, Hume, and Wineland at NIST measured the same effect in Science in 2010 across a height difference of 33 centimeters. The escape routes are all closed. It is a perceptual illusion from signal delay. The effect survives after light travel time is subtracted. It lives in the coordinates, not the seeing. A preferred frame we have not yet located. Modern Lorentz invariance tests constrain violations to parts in 10 to the 17th. It cannot matter at walking speed. Roger Penrose worked the numbers in The Emperor's New Mind in 1989. Two people walking past each other have surfaces of simultaneity at Andromeda that differ by days. And philosophy made it worse. Reitdijk in 1966 and Putnam in 1967 argued that if relativity holds, the future is already as real as the present. Nobody has refuted them on their own terms. A person walking towards you and a person walking away disagree about whether tomorrow has happened yet. Both are correct, and over the 33 centimeters between your feet and your head is aging faster. Measurably, if every observer carries a different now, which one is the moment you are actually in? Time turns out to depend on the observer. Temperature turns out to have a memory. Number 4. The Mpemba Effect. In 1963, Erasto Mpemba was a schoolboy at Magamba Secondary School in Tanzania, making ice cream in a cookery class. Freezer space was shared and scarce. Rather than wait for his mixture to cool and lose his place, he put it in hot. Newton's law of cooling makes an unambiguous prediction here. A hot sample must pass through every temperature the cold sample starts at, on its way down. To freeze first, it would have to overtake itself. This is not a subtle forecast at the edge of a theory. It is arithmetic. The hot mixture froze first. His teacher told him he was confused. Mpemba repeated it with plain water and got the same result. Mpemba and Osborne published it in Physics Education, Volume 4, 1969, comparing samples at 70 degrees Celsius and 25 degrees Celsius in a domestic freezer. Aristotle had described the same claim in the Meteorologica. So had Francis Bacon. So had Descartes. 3 of them, ignored for 3 centuries. Then 2 centuries of explanations, each one insufficient. Evaporation of the hot sample, measured, too small in sealed containers. Dissolved gases driven out by heating, results conflict across laboratories. Convection currents, partially predictive, never universally. Supercooling, from David Auerbach in the American Journal of Physics in 1995. Hot samples nucleate ice earlier, which helps and does not cover every case. Hydrogen bond energy storage, from Zhang and colleagues in the Journal of Physical Chemistry C in 2014. Then Burridge and Linden ran it carefully in scientific reports in 2016, could not reproduce it, showed the result flips with thermocouple placement, and concluded the effect is not real. Then Kumar and Beckhofer saw it cleanly in a single colloidal bead in a shaped optical trap in Nature in 2020. And Aries, Murciano, and Calabrese found a quantum version in Nature Communications in 2023. Cooling is not a slide down a number line. It is a path, and the path remembers where it started. Your kitchen thermometer cannot see that memory. What else in your house is carrying a history that none of your instruments can read? Heat behaves strangely. Now consider what happens when you simply break something. Number 3. The sugar that emits X-rays. In 1605, Francis Bacon, compiling the Advancement of Learning, was cataloging minor natural curiosities of the kind gentlemen noticed and wrote down. Among them, hard sugar, scraped with a knife in a dark room, gives off sparks. He offered no explanation. A note, not an experiment. Breaking a crystal is a purely mechanical event. Bonds snap, a little heat is released, the pieces separate. Nothing in that description produces light. Nothing in it produces anything more energetic than light. Crush a wintergreen sweet in the dark and it flashes blue. Peel ordinary adhesive tape in a vacuum and it emits X-rays. Jeffrey Zink identified the sucrose mechanism in accounts of chemical research in 1978. Fracture drives an electrical discharge in the nitrogen around the crack, emitting at 337 nanometers. And the methyl salicylate in wintergreen absorbs that ultraviolet and re-emits it as blue. Then Camara, Escobar, Hurd and Putterman at UCLA published in Nature on the 23rd of October 2008. Peeling a roll of Scotch tape at about 3 centimeters per second under a vacuum of 10 to the minus 3 torr produced nanosecond X-ray bursts, photon energies up to 100 kiloelectronvolts. Roughly 1 billion photons per burst. Enough to radiograph a human finger. They published the image. The mechanism is still open. Piezoelectricity. Many triboluminescent crystals are centrosymmetric and not piezoelectric at all. Gas discharge, the tape works in vacuum, and some materials glow in inert atmospheres. Thermal emission, the spectra are not thermal. Linda Sweeting at Towson University spent 2 decades cataloging which crystals do it, and her 2001 review in Chemistry of Materials concludes that 1/3 to 1/2 of non-centrosymmetric crystals are triboluminescent, and no rule predicts which. Charge separation is involved. How it separates is not. A sweet in your mouth in a dark room is running a small electrical discharge against your teeth. A roll of tape in your drawer can produce ionizing radiation. If something this energetic hides inside a sugar crystal, what is hiding in every material nobody has thought to break in the dark? Sugar makes light. Storms make something considerably harder to define. Number 2, the ball lightning spectrum. In July 2012, Jianyang Chen, Ping Yuan, and Simon Shui of Northwest Normal University were on the Qinghai Plateau with slitless spectrographs and high-speed cameras, recording ordinary cloud-to-ground lightning. A routine field campaign to measure the emission spectra of strikes. Nothing there was designed for what it caught. A lightning channel lasts a few milliseconds. Plasma at those temperatures dissipates the instant the current stops. A glowing object that persists for seconds, drifts horizontally and keeps its shape, has no place in atmospheric electricity, and for 2 centuries every report of one came from eyewitnesses alone. One sequence caught a luminous sphere forming at the strike point, drifting roughly 15 meters, lasting 1.64 seconds. They had it on camera, and for the first time in a spectrum. Sen, Yuan, and Sui Physical Review Letters, Volume 112, 2014, the spectrum showed silicon, iron, and calcium, the elements of the soil where the bolt landed. It supported a proposal from John Abrahamson and James Dennis at Canterbury in Nature in 2000. Lightning vaporizes silica in the ground. Silicon nanoparticles condense into a filamentary network, and the network burns slowly in air. That still leaves most of the phenomenon unexplained. An antimatter meteorite, proposed by Ashby and Whitehead in Nature in 1971, ruled out by the absence of annihilation gamma rays. Microwave radiation trapped in a plasma cavity, Otsuki and Ofuriton made glowing spheres in a cavity in Nature in 1991. Never in open air. Nanoparticle combustion, which fits the Qinghai spectrum but not the repeated reports of spheres inside sealed aircraft cabins in closed rooms. And Peer and Kendall, in Physics Letters A in 2010, proposed that some indoor sightings are magnetophosphines, the pulse from a nearby strike stimulating the observer's visual cortex directly. The same mechanism as transcranial magnetic stimulation, which would mean that part of this phenomenon has no external existence at all. 2 people in a room during a storm could see the same sphere, and one of them could be seeing it from inside their own head. How do you build an instrument for an event that may be occurring in the observer rather than in the room? The last entry is not rare, not disputed, and sitting inside your phone. Number 1. The Casimir force. In 1947, Hendrik Casimir was at Philips Research Laboratories in Eindhoven, working on a commercial nuisance. Colloidal suspensions in Philips products were not behaving the way van der Waals' theory said they should. He described the problem to Niels Bohr on a walk, and Bohr muttered something about zero-point energy. The setup is the emptiest possible one. 2 uncharged, non-magnetic metal plates parallel in a vacuum. No fields, no charges, no medium. Nothing that could push them either way. Casimir calculated that they attract, not through any field you can point to, through the vacuum's own fluctuations, the longest of which cannot fit in the gap. Casimir, Proceedings of the Koninklijke Nederlandse Academie van Wetenschappen, Volume 51, 1948. The force per unit area scales as 1 over the separation to the 4th power. Steve Lamoureux measured it to within 5% in physical review letters in 1997, at separations of 0.6 to 6 micrometers. Mohidane and Roy reached 1% in 1998. Chan, Axiuk, Bishop, and Capasso used it to drive a micro-machined torsional device in science in 2001, empty space operating a machine. And the interpretation has been collapsing ever since. It proves vacuum energy is real. Robert Jaffe at MIT showed in Physical Review D in 2005 that the whole effect follows from relativistic van der Waals forces between charges in the plates, with no zero-point energy invoked anywhere. Then vacuum energy is not real, field theory still requires it, and the Lamb shift is confirmed to 12 significant figures. Then add it up and check it against the sky. The density field theory predicts exceeds the observed cosmological constant by a factor of 10 to the 120th power. The worst quantitative prediction in the history of physics. And in 2011, Wilson and colleagues reported in Nature that moving a boundary fast enough in a superconducting circuit produces real photons out of nothing. The accelerometer in the phone in your hand is engineered around this force. At those separations, Casimir attraction can weld moving parts together permanently. Empty space is a component in your phone. Something with no substance is pressing on you at every scale, and our number for it is wrong by 120 orders of magnitude. What is a vacuum? None of these sit at the frontier. Everyone sits inside the parts of physics we trust most: the double slit, Newton's law of cooling, the meaning of the word now, the vacuum itself. The universe is not confused. It runs without contradiction, without hesitation, without a missing number, in your kitchen, tonight, while you sleep. The confusion is entirely on our side of the glass. Reality has never been strange. Our account of it has. If you want to see more videos like this, click the video on screen now.